to the next lecture by Mr. Malekpour from GE Digital USA.
Thank you so much. Thank you so much, Dr. Fereidunian, for having me. Can you hear me?
Yes,
hello.
Yes,
can you hear me?
Yes.
Perfect.
Yes.
Perfect. Just a quick disclaimer, should my audio degrade at any time at this session, please let me know. I'll pause for a moment and then hopefully it can come back to us. There have been some internet issues in my neighborhood recently. Not the best time for it, but not like I can control it. I appreciate sharing your screen. Wonderful.
Yes.
Thanks everyone for joining. My name is Ahmad Reza Malekpour. I am a staff data scientist within GE Digital in San Ramon, California. I'm responsible for developing machine learning and AI product suites for GE Digital. My research and work background, goes back to my postdoctoral position at MIT, as well as manager of grid strategy and analytics at ComEd, the largest electric utility in Chicago, Illinois. In this talk, I'm going to talk about the data analytics and how it supports situational awareness for electric car grids by introducing a couple of GE grid analytics products. Not to mention that electric power grids is one of the key infrastructure as part of the smart cities. This is a typical disclaimer that we put for outside slides. If you go to the next slide, please. Yeah, here is a quick overview of the agenda. I'll be talking about the electric grid and various changes that happens and are going to happen at different levels, including big data analytics. And then we will talk about some of the key enablers for analytics to happen as it relates to enabling situational awareness in electric power grids. A little bit more about GE and its footprint in the grid, followed by GE's vision for transforming to a digital grid. Moving on, we'll talk about GE's grid analytics team, the three products at high level, the overall analytic architecture will be discussed, and then we'll dive into the network connectivity product, discussing more details about the problem at hand, why is it important, what methods have been used to solve, etc., etc. And we'll wrap up by Q&A, hopefully. Next slide, please. Cool. This is an overall overview of what we call traditional, typical electric grid. Starting from the left, you see large generation stations typically located close to either fossil fuel or other resources generating power at high scale. And then we have in the middle transmission line, high voltage to carry power from the power station to major load centers and cities. And then we have distribution systems, basically distribute power to commercial, industrial, residential areas through lower voltage distribution lines. And basically the analytics that I'm going to dive into and talk about is going to working on distribution system side. In this setup, typically approach is to increase the number of power station in response to a load growth if happening within the grid. On one side, power grid becomes more mature and dependent on electricity for heating, cooling, communication, banking, right? A lot of other customers, need it, and it's on the growth. And customers today are demanding higher level of reliability and power quality. So there's a lot of demand from the customers as far as getting better services. On the other side, you had electric utilities where they're highly regulated and historically have little competition. No competition means that a lot of inefficiencies. But in the last decade, there has been a lot of pressure and movement toward decarbonization along with using distributed energy resources in the grid. If you go to the next slide, please. All right, addressing some of the concerns, some of the grid, issues. The grid is aged. It's designed 50 years, 100 years even before aid, asset, and infrastructure and workforce. Right, a lot of old engineers. And one of the goals of electric utilities through grid modernization project was to address these. It's been tackled through, for example, pole replacement, reconductoring, and also employing new hires. And we see installation of large-size solar and wind, as well as other small-scale renewables, even rooftop solar at the home levels. And also bringing, renewables, meaning that there are a lot of challenges with variability associated with them. They're not providing power 24/7, right? And these variable energy sources are bringing a lot of issues like voltage violation, voltage variation, and whatnot, to name a few. To address these changes, there was a need for storage, power storage, basically storing power when it's needed and addressing those variabilities. And another thing is that those customers that used to be prosumers, now they're becoming consumers. Consumers, now they're becoming prosumers, meaning that they're able to generate power and injecting back to the grid. All in all, grid was not designed for all of these changes. So traditional distribution system operators had very limited visibility beyond what we call distribution substation, where all the feeders coming out and all the low voltage distribution feeder is there. So it was not unusual for electric utility to have like insufficient information about network and phase connectivity in their distribution system. This resulted in a limited situational awareness at distribution systems. That's why majority of the devices, operational devices such as smart inverters, rooftop solars, protection devices, and even smart meters are coming to the grid with data collection, measurements, and communication capability, meaning that they have been increased in the number of collected data, and the purpose is to increase the monitoring and controlling the power grid at the lowest level, basically even at the home level. And utilities start to see that there are a lot of data coming to them. For sometimes the grid was on one side and the big data on the other side were two separate silos. Now you can see it will cause a lot of inefficiencies. Now utility realizing that this data can be used to making grid more efficient, and they're excited to using a lot of analytics within their portfolio. Next slide, please. This slide shows deployment of smart meters according to the U.S. Energy Information Administration, EIA. See that the deployment is on the rise, actually. I'm not going to go on it for interest of the time. I'm not going to go through all the numbers. But just to highlight that the installation of smart meters is on the rise in the US and across the world. And these installations contribute not only to improving the energy billing, which was the main purpose of having a meter at home, but also to increase the situational awareness of the distribution system beyond distribution substations. Next slide, please. Another enabler, I would say, was the need for investment, right? DOE has tremendously proposed different plans to invest in a lot of merger infrastructure, not only grid. As you see that it's in 2020, $40 million for artificial intelligence, machine learning across scientific different disciplines, but infrastructure grid is one of them, and that helps electric utilities, researchers, national labs to work together to come up with the methodologies and new analytics to use these data and make them these big data to actionable items for electric utilities. And we believe that this could potentially provide situational awareness, help monitor improvements for reliability, security, customer satisfaction, and whatnot. GE has developed 3 analytics, mainly network connectivity, storm readiness, and historical outages to help those electric utilities how to handle their big data and how to run their electric grid more efficiently. Next slide, please. Can you guys see next slide? I can't see it. I think, yeah, cool. Talking about GE and the grid, GE is a big player in grid and has established itself, as a leading technology developer and manufacturer with a valuable installed base and expansive global reach, more than 140 countries worldwide. GE generates about 1/3 of the world's electricity and has about 1,600 gigawatts of installed capacity. Here, their gas is their GE's largest segment remaining as the part of their world, long-term power generation mix. And about 40% of the world electricity use GE software for either operation, maintenance, monitoring, diagnosing, and whatnot. And about 90% of transmission utilities worldwide are equipped by GE. So, and not to mention that with the growth in overall renewable market, GE is expanding its market share into that area as well, with offshore winds and storage. So it's quite obvious for GE to have a foot in it and then invest in analytics in this area. If we can go to the next slide, please. And this picture shows GE's vision for digital transformation of electric grid and where different analytics may land depending upon the difficulty of the problem to solve and value it's bringing. Basically, on the left low side is the lowest value and easiest problem to solve. Well, the analytics is more reactive, just saying, okay, what happened? A fault happened, okay, what happened? A fault happened, for example, all the way to having an autonomous grid where the aim is to have a self-healing, self-provisioning grid with more like operators hands-off, being able to handle itself without or with limited human intervention. We have some analytics that are going to land somewhere in between, either predictive, prescriptive, or sometimes the first 2 steps are called descriptive, that we have those at our portfolio. If you can go to the next slide, please. Cool. So this is these are the 3 analytics products to help electric utilities. Storm readiness is basically saying that it's working through for the extreme event days. For example, a storm that happens typically in Chicago area, or a storm happening in Boston area, a storm happens in any part of the world. We had a storm recently even in Texas area. Nobody believes that's going to happen. So it says that I'm going to look at the next 72 hours and tell you where to position your crews in order to jump into the grid when outages, when the storm hit the grid and outages happens. Basically positioning the crew in advance 72 hours. A crucial for electric utilities, very demanding. The next one is network connectivity, basically saying that how meter and transformers are connected to the grid and how we can update a lot of inaccuracies in the databases that are currently being used, and it's being used as a source of truth for other analytics as well. This is the one that we're going to dive into shortly. Next one is historical outages, saying that given the outages, tell me what kind of engineering solution I should implement to prevent outages in the future, basically. Yeah, if you can go to the next slide, please. This slide shows the overall architecture of these analytics. The picture on the left, basically, starting with the left side, operational technology shows, that the data that feeds into the historian. These operational technologies include GIS, outage management system, OMS, distributed energy resource management system, DERMS, distribution management system, DMS, energy management system, EMS. On left side and on the right side, we have advanced metering structure, customer information systems, mobile, and whatnot. And below is just the sensor relays and other controllers that are sensing the data and can feed data into the heart of this database, basically information hub. It's a data historian that any of new analytics can tap in and use those data for their purposes and use cases. Basically, we realize and learn that we can't go project by project. We used to have a lot of customers coming to us saying that we need analytics and these are the data set that we have. Some limited data set, right? And then we created a platform for that, and then they used it, they left, and another customer comes with it truly different requirements. So GE had decided to have, as a product, putting a product lens and saying that we need to have a common database that reducing a lot of operation costs as far as the software engineering. If you can go to the next slide. Cool. We're talking about network connectivity. Moving on. Network connectivity has two main algorithms. One is more concerning about meter to transformer association. The picture on the right shows two transformers, T1 and T2, and 6 meters. M1, 2, and 3 are connected to T1 in the database, and 4, and 5, and 6 are connected to T2 in the database. But if you go into the field and in reality you see that, oh, wait, M2 is connected to T2, but in the database, because there are a lot of manual insertion of data and errors in the databases, M2 is shown that's connected to T1, where in reality it's connected to T2. So a lot of, if you look at the different utilities, you see that sometimes something between 40% to 90% inaccuracy you see that in their GIS databases. And typical approach for the utility, typical processes that they follow is that the operations or engineering through updating a device, through a new upgrade that they want to do, or even through outage management. When they go to the field and realize, oh, this meter should be connected, M2 should be connected to T2, and they communicate it back to their data maintenance department. Obviously very, limited when you're talking about a utility that has millions of the meters and hundreds of thousands of transformers. Apart from that, the challenge is that there are a lot of new devices coming and the data volume and quality is of great need. This data set is being used for rolling out the trucks when the outage is happening. And basically, we're sending the truck to the wrong place, delaying responses to the outages, putting the customers at risk. Not only it's also impacting analytics like this, the outages and addressing the outages. It's also a source of data truth for any application like distribution energy management system, voltage control, or others. So it's going to impact the results of all those other applications. And obviously, manually fixing all of these is, if it's not impossible, it's exorbitantly expensive. These are the challenges that utilities seen, and there was the need for this analytics. If we can go to the next slide. So the problem at hand is that we really want to make corrections to those meter to transformer associations using the data, using the available data, minimum sets of data set that they have. Some utilities roll out their AMI, some utilities that some of them doesn't have, for example, voltages. So using the minimal data set that we have, can we build an analytics and address this concern? And why is it important? It's reducing their outage operation and maintenance costs. Excuse me. As well as, once you roll out the truck to the right places, it's going to restore the outage as fast as possible, provides customer satisfaction. As I mentioned, it's going to help readiness, data readiness for other applications like advanced distribution management systems, and increase, situational awareness for transformer sizing and estimating of electric vehicle hosting capacity. Basically, you're saying that if I want to put more load on a couple of houses, can the transformer that are supporting those houses handle those additional loads or not? With, wrong databases, you cannot basically say that, because you're aggregate a couple of more meters probably, and you're saying that this transformer cannot handle more, where in reality it can. Next slide, please. The second algorithm under network connectivity is transformer to phase association. If you look at the picture on the right side, a typical feeder lines, around your house, you see that there are 3 lines ABC, and a transformer is connected to one of those phases, and there's a secondary line coming to your houses, supporting your houses through the meter. A lot of these transformer to phase associations are typically missing or inaccurate. So the aim is to develop an analytics to relabel basically the transformer to the correct, phasing through the databases. And it's just very important for utilities because load balancing is the major one. In case there is a development in an area, they want to put a transformer with a couple of homes supporting, how can, which phase that transformer should be connected to. So those, and the aim in distribution grid is to make things balanced. Basically, you want to balance the load between all those 3 phases. The other applications are 3-phase power flow or optimal power flow that's going to get impacted with phase. Volt for control, where I've been involved in one of the major projects, voltage optimization at ComEd, Illinois, where we face this issue when we look at the consumption at the head of the feeder versus when aggregating all the meters in that feeder. We've seen a gap between the two, and we realized that some of the meters are some of the transformers are mislabeled, and it will greatly impact the result that we were looking for. Another major application is distribution network reconfiguration and restoration that needs the right phase labeling. Next slide, please. Network connectivity is using two source of data, kind of two analytics. One is geospatial, the other one is more data-driven. Geospatial is more concerning about what's the distance between the meter and transform, basically working with the coordinates and trying to have a statistical analysis about the distances and the populations in different areas, urban, non-urban areas. And also some geospatial features between the transformer or meters, like rivers or highways. The other one is more data-driven, where we look into the outages, where both meter and transformer can have different outages. And voltages, measurement at the meter level that can be used, as well as, the grid itself, the grid structure, the connectivity between the nodes and that are forming the deep feeders are of great importance. Next slide, please. Perfect. So how will meter to transformer mismatches will be identified? It does have 4 separate analytics. One is distance analytics. Its primary factor for mismatch when the meter to transformer distance relation is greater than a designated basically threshold. Distance threshold is calculated for each transformer based on its pair meters. And the meter population density is very important here, which has been taken into consideration. So once the mismatched meters are identified, basically saying that this meter is very far from that transformer, so that cannot be connected to that transformer. And then flag that as a mismatched meter and try to look at the nearby transformers and map it to a new transformer that is in the shorter distance. We call that the new transformer is a recommended transformer. Basically, the algorithm has 2 steps. One is flagging something is wrong. The other one saying, okay, something is wrong. What should we do for that? I'm saying that this meter is not connected to that transformer, so which transformer it should be connected to? The other one is land-based. Basically, electric connections in low voltage distribution system are designed in such a way to avoid land-based features. Either natural or man-made obstacle like railroad, waterways, highways, bridges. You won't see, a meter line connecting a meter to transformer over these obstacles. So if such an infeasible geofeature presents in the database, that meter is likely mismatched. So it will look into number of those interactions of the meter transform page with those infeasible geospatial features, and will flag them as a mismatch. And for obvious reason, this one cannot recommend a transformer because it's just using the geofeatures. The other one is basically outage analytics. If you look into the outages that are transformers experiencing, as the meters under that transformer, and saying that if I confirm an outage on transformer side, I'm expecting all the meters connected to that transformer to be out of power. If one meter is not experiencing outage, it's probably not connected to that transformer, and flag that as a mismatch. And obviously, it will reconnect it to a recommended transformer that has highest, outage correlation with the meter. Same thing for the voltages, but here the difference is that we do not have measurements at the transformer level, versus we do have measurements at the meters. Meters are measuring the voltages, so a pseudo voltage has been created for the parent transformer, and the correlation between that voltage and the meter are used. The correlation is low, the meter is identified as a mismatch, and it's been remapped to a recommended transformer that has higher, correlation, voltage correlation. Next slide, please. The next one is basically how transformative phase mismatches is identified. This one is purely data driven, and we look into the voltages at a meter level. On the right side, you can imagine that we have three-phase voltages on two different meters, those two columns. And basically, it's trying to cluster and saying that, hey, I believe these two voltages are presenting the same signature. So clustering them together and saying that these meters should be on the same phase and assign a phase for that. And this has been done through machine learning algorithms to identify the new labels. Next slide, please. This slide shows, see some product UI pictures for a customer in North America. And it does have an interactive UI. You'll see at the back end on top, when you log into the UI, you see an interactive map of electric utility with some general information about number of mismatches in each area that you can zoom in and search more. It does have a data analytics tab that shows a list of mismatch meters in a tabular format, basically the picture in the middle. And each row of this table shows you the mismatched meter ID, the current transformer ID, the recommended transformer ID, which analytics flag this as a mismatch, which analytics recommended as the transformers, and some confidence level from the analytics perspective about these flaggings and recommendations, the meter addresses, and many more. And then the picture at the bottom actually basically there's a network viewer tab that visually shows the map of the current transformer. At the bottom you see a yellow rectangular, that's the current transformer. What you see in red, those are flagged as mismatched meters that are connected to that. And the recommended transformers are connected through these meters through blue lines. And what you see in green saying that, oh, those meters are connected to the current transformer, then they are good to go. There are no problems with them. So some solution capabilities have been presented here with the ingestion of a lot of data set like GIS, OMS, AMI, CIS for error detection, which improves this, we call it source of truth, because a lot of other application and databases are going to use the meter transformer associations and fate labelings. So current transformer to meter error detection has been used to improve responses to outages, whereas transformer to feeder and phase data has been used to improve OMS and distribution management system and any new analytics. And it does have the capability to correct upon selecting a business rules, proactively catching errors as they occur, and continuously improve the source of the data. If you can go to the next slide, please. This slide outlines the application outcome of the network connectivity analytics. Starting from the top, it increases the public safety as we discussed. It will help, rolling out the truck to the right places, addressing the outages as fast as possible, and reducing the risk to customers which are experiencing outages. Outage response cost has been reduced with sending the crew to the right places again, reducing the operation and maintenance of another key components are some reliability matrices, SID and KID. The first one is more about interruption duration for the system level as well as the customer interruption duration. It tries to improve those. Those are the key reliability metrics that is mandated typically from the legislation for each electric utilities. So we believe that this NC analysis could potentially provide situational awareness, helping electric utilities, run their grid more reliably, securely, providing public safety and customer satisfaction. So basically providing, value both to electric utilities and the customers. With that, this ends my presentation. Would be happy to answer any question in the Q&A session.